All right, BNS 210. As I go through my background of 80s movies, here we have Sarah and Luda from Labyrinth, another one of my faves. Okay, so this PowerPoint, I'm going to talk about power, and then I'm going to talk about confidence intervals, and then this is it. Yay, and then I'm going to send out the quizzes, and we'll be good. Okay, so you remember a long time ago on one of those PowerPoints where I talked about a type 2 error, and I talked about it being how I talked about a type 1 error being represented by alpha, and I talked about a type 2 error being represented by beta, and to put a pin in it, here's where our type 2 error comes in. So the power is also known as our risk of committing a type 2 error. You can kind of think about it as the opposite. I'll show you the equation. It's like the inverse of it. So the more powerful your experiment, the better able you are to avoid a type 2 error. So remember, a type 2 error is whenever there is an effect out there. There is significance out there. You just weren't able to find it. So what you're looking for is real. It's a real thing in the population, but for one reason or another, you didn't get there. Usually you don't get there because you didn't have enough participants. So usually it's because of a small sample size. The greater your sample size, the more likely you are to find something that there is, if there's anything to find. And so therefore, the larger your sample size, the more powerful your experiment is. And this makes sense, right? Because we're thinking about the general population. And if you want to know, say, going back to our disordered GPA example, if you only test 2 people with a psychological disorder, you're a lot less likely to find that they have a low GPA and they'd be representative of the population than, say, if you tested 100 or 1,000 people that have a psychological disorder. So sample size certainly affects power, and your effect size also affects power. So again, the bigger the effect out in the world, the easier it is to find it. So if GPA really is affected by psychological disorders, and people with psychological disorders really do have a lower GPA, and most people that have a psychological disorder have a low GPA, then you don't need to test as many people to find that effect, because it's out there, it's real, it's a big effect, so you don't need as many people. If you have a small effect, let's say only 20% of people with a psychological disorder have a lower GPA, then you have to find a lot more people to test that. So that's what power is doing for you. So Cohen, who is the big stats guy, and he was the one that came up with kind of a lot of these ideas behind stats, if you're interested in the history, which I'm not. But nevertheless, he decided that making a type 1 error was a lot more serious than making a type 2 error. So in this instance, he decided that making a type 1 error was 4 times more serious than a type 1 error. So we're only going to give ourselves 5% risk. We have to be 5% or lower of our risk of making a type 1 error. But for beta risk, we're going to give ourselves up to 20%. And this is related inversely. So we want to make sure that our study has at least 80% power. Most of the time, most scientists are okay with 78% or higher. So this means that 78% or 80% of the time, you're going to be able to find an effect if there's one to be found. Okay, so there is a program, it's called G-Power. It is free to download. You are welcome to download this and play around with it. Power is really only beneficial before you run an experiment. What it really tells you is it tells you how many people you need in your study to find significance. So here's an example, and here on G-Power, you could choose whether you're doing a t-test or an f-test or other types of tests, and then you can choose what your statistical test is. And then you can select a priori. You can also see what your power is post hoc after the fact, but a priori is a lot more powerful. So we're going to do this. We're going to have a 2-tailed test. We're going to say that we want at least a medium effect size. We're going to set our alpha at 0.05. And then, of course, we want 80% power. And then we hit calculate. And this is what it'll give us. It'll give us all of this over here. So you could see that it'll tell us what our degrees of freedom is going to end up being. It'll tell us what our critical T needs to be. It'll tell us that we need at least 64 participants in each of our levels. And so our total sample size needs to be 128 participants for us to get 80% power in this particular example for a medium effect size. If we put a bigger effect size, then this number is going to go down and we won't need as many people to find it. So here we have an 80% chance that if there's an effect to find, we will find it. So we have a 20% chance of committing a type 2 error in this example. Okay, so that is power. So now I'm going to use the same example here to talk about confidence intervals. Confidence intervals are a little bit harder to understand in my opinion. In one of these slides that's already posted, I have a really great paragraph that really explains it really well, I think. So hopefully that'll help. And of course it explains it all over the internet and things like that, possibly better than me. Confidence intervals is one of those things I intuitively understand, so hopefully I can explain it to you. Okay, so if we go back to our psychological disorder example, remember that there is a true population mean out there. We just don't know what it is most of the time, but there is a population mean out there, okay? So let's say for psychological disorders that the population mean is 2.3. That's the average mean of college students' GPA in the entire world. So that would mean that if we take our control group, right, these are people without psychological disorders, then let's say the people that we polled are 2.6, that's their GPA. So that's pretty close, right? That's pretty close to the population mean. And then we have our disordered group, which is significantly different from both the population mean and our control group. So our disordered group has a significantly lower GPA compared to our control group. Now, again, most of the time, like, we're not going to actually know what the population mean is. So what SPSS does is it estimates it for us. And that's where confidence intervals come in. Confidence intervals tell us with 95% confidence that the real population mean is within a certain range. Okay, so this depends on your alpha, and it complements your alpha level as well. So if our alpha level is 5%, then our confidence interval is going to be 95%. If our alpha level is 1%, then our confidence interval is 99%. That means we could say with 99% confidence that our population mean is included in some range of values. Okay? So that's what a confidence interval is telling us. And again, most of the time our alpha is going to be set to 0.05, so therefore most confidence intervals are going to be 95%. Okay, so here's what it looks like on an ANOVA. So here we have our mean of our grand mean, for example, in some study. So this is all of our participants, our grand mean is 50.44. So what this tells us is that somewhere in the population, that the population mean is somewhere between 33 and 66. We are 95% sure that the mean, the grand mean, is between 33.9 and 66.9. So then if we go down to like another example where we have a D2 antagonist and we have, say, saline, and we have, so this is the example I gave a while back with locomotor activity and a D2 antagonist. So this is saying that if we gave everybody, all of the birds in the world, saline and measured their locomotor activity, that it would range somewhere between 62 and 112. This is the same thing here, okay? So this is telling us what our confidence is that our, what the population mean out there is. Okay. So in this example, here's an example where we have, this is a paired samples t-test, this is a within. So this looks different in a within test. So what I was just showing you is a between, and what that looks like for a between. I also want to point out, let me go back. Okay, so one thing I want to point out here is that you'll notice that none of these confidence intervals include 0. Remember when we're working with a standard normal curve, and we're thinking about the Z distribution, okay, that a Z distribution can include 0. And if we have a 0, that means there's no difference in the population. So if we're looking at something like this, ideally we want our confidence interval to not include 0. Because if it includes 0, that means that there's not going to be a difference in our groups. So here we have this example where we're looking at a paired samples t-test. And what this test is looking at hiccups. Okay, so it's looking at how many hiccups, and if you don't have any intervention versus if you do a carotid artery massage. Okay, so hiccups per minute was 13 for people that didn't get the carotid artery massage, and those that got the carotid artery massage had an average of 8 hiccups per minute. So we look at this and we can see what the standard deviation is and what the standard error is. So because we're dealing with the within, we are going to subtract these two from each other, right? And the mean difference between these is 4, okay? 4 hiccups between these, okay? So when we're looking at the confidence intervals, on average, in the population, that people that received a carotid artery massage are going to have somewhere between 1 and 7 fewer hiccups than baseline. And then this is how we would write the full APA format, including the confidence interval. This is how we'd write it for a t-test. Okay. So here we also have our pairwise comparisons where we're looking at the differences between one group and another. And again, we're looking at mean difference whenever the confidence intervals are being examined, and we're looking at post hoc tests. So this is a chart of post hoc tests. And you'll see here, okay, so if the difference between these is 0, that means that there's possibly no difference between these groups, and that in the population, there's possibly no difference. So you'll notice that in these intervals that include 0, like this one, you don't have significance. Because there's a chance that there is no difference between, say, 0.3 milligrams aticapride and saline out in the real world. So if these don't include 0, then you're more likely to see significance, because that would suggest that in the real world, there really is a difference. 0 is not included in that confidence interval. So that's confidence intervals. So just to sum up all of stats and the things that we care the most about is, of course, we care about the p-value. It tells us what our significance is. This tells us if an effect is likely to exist in the population and how likely we are to reject the null hypothesis with confidence. How likely are we to make a type 1 error? An effect size will tell us how big this effect size is in the population. What percentage of the population actually is likely to experience this effect? And then power is going to tell us, it's best used before you run an experiment, is going to tell us how many people, how many participants we need to include in our study so that we can feel confident about our results. How likely are we to find an effect if there's an effect there to find? And then confidence intervals give us an estimate of what the real population is out in the real world. So those are the 4 main things that we need to know in stats. And that's all, folks. Thank you once again for watching another one of these videos. Signing off. See ya.